All right. Last time we introduced the concept of context-free languages. We talked about why these might be important. So this maps to programmatic constructs by taking some A's and B's. And you can map those to open curly braces and closed curly braces. We looked at the concept of a context-free grammar, so we went over what regular grammars were. So we were relaxing this concept of needing to have our non-terminals at one end or the other. We can now say non-terminals can appear in the middle. Here was an example of a context-free grammar. We looked at it, some possible strings, the language it represents. We found that it was WWR, a string followed by that same string in reverse. We talked about whether it would be possible to produce this language with a regular grammar, and we determined that no, it would not be possible, mainly because instead of tackling this from the middle, we have to tackle it from the left or right, which requires us to know how many A's and B's and in what order we produce them. Whereas if you're able to add in the middle, now we can take a more recursive approach to this, where we recurse in the middle rather than recursing at one end or the other end. So this is possible when you allow for that. Then we ended with this grammar. Produce a grammar for this language, A to the N, B to the M, where N is not equal to M. So I want to go over what people have thought about since yesterday's class. Did anyone come up with a solution?
I think so.
Yeah? Talk me through it.
So we have a phase here. Let me pull this up real quick.
Yeah.
We have a start of A or B, and that A or B is non-terminal.
So A or B.
Yeah, and then defining A, we can do a singular lowercase a or go back to A.
Or go back to A.
Yeah, or like just capital A.
Yeah.
That'd probably be easier to just say it like that.
Yeah.
Or lowercase a, capital A, lowercase b. Or lowercase a. And then the capital B is capital B, lowercase b. Or a capital B, lowercase b. Or lowercase b.
Interesting. So the idea is that once you're in A, you can't get to B. And once you're in B, you can't get to A. So we need to split this like an if statement that says, are there more A's or are there more B's? If they're not equal, those are the two cases that can exist. There are either more A's or there are more B's. In this case, we can produce A's to terminate the grammar because there are more A's than B's. That's the only way to terminate. We can make an equal number of A's and B's, but we can't terminate until we make an A without that. And this production allows us to loop this and say there are an arbitrary number of more A's than B's. I think that covers all cases for there being more A's than B's. This lets you produce an arbitrary number of B's as long as there is an associated A with it, and then an arbitrary number of more A's than B, and at least one more A than B to terminate the grammar. So there's no way to terminate this having A's and B's being the same. You just have the exact opposite on this side. There is one other consideration, which is, are all of the A's forced to be on the left side of this? Because we know that all of the A's come before all of the B's. So this is the correct way to do this. We want to add in the middle because we could loop this and then produce this. And if we do this, we want the B to come after this A that was produced. So this is a necessary ordering for this part of the production because these terminals need to come before the adding in the middle. So I buy that regardless of the order that you do this, all the B's come at the end and all the A's come at the beginning. The first part and the second part. So looking at this last set of productions, now we're forcing the B's to come at the end. So we do have to flip exactly like this, so that we add in the middle and we're forcing the b's now to come at the end. Which is why this non-terminal has to come before the terminal. Does that make sense to everybody else as well? We can still produce an arbitrary number of a's and b's, but the b's have to come at the end, the a's have to come at the beginning. If we have an arbitrary number of more b's than a's, those b's also have to come in the second part. And then the b that we add terminates it at the end.
Could you do A capital A B and then A capital B B?
So what's the string that you are saying to be generated?
A B A B
A, B, A,
B B.
B, B. All right, let's see if we can do it. So
The second and the fifth would become capital A, capital B.
this, you have to choose one or the other. You can't have both.
So both of together?
Yeah,
Oh,
this is A or B. This kind of tells you whether you are in the case of more A's than B's or the case of more B's than A's. Yeah, great idea, but I think that this is not possible to generate in this grammar. Other thoughts or questions? Any issues that anyone sees? I like it. I think this works. I also love it because it's different than the answer that I'm about to reveal. So here's another solution. It has a lot of the same components, but it's structured a little bit different. We're saying that there's some commonality between these two productions. So we can factor them out into something that says we can repeat those an arbitrary number of times. And then the A in this grammar just produces A's at the front. This B just produces B's at the back. And then we have an arbitrary number of A's and B's in the middle. I think this solution is more intuitive. Easier to see what's going on here. Here's another answer. Yeah, it's hard to produce more B's than A's here, isn't it? No, there has to be one more production that's missing here. Yeah, I don't know what's with that, that's wrong. Questions on either this solution or the first solution over here, both of those are certainly right. But this would work for something that said more A's than B's. A to the N, B to the M, where N is greater than M. That would get you there. Not for this problem. Questions? Does it make sense how this solves the problem? Does it make sense how that solves the problem? Everyone able to kind of make that connection between this language and generating a grammar that where this is complete, it produces everything that could be in that language. All infinite possible strings that could be in that language. That's a really interesting. As you start thinking about context-free grammars, they start getting a little bit more complicated, as well as you can start seeing how a finite and even small number of productions can produce an arbitrarily complicated, an arbitrary number of strings and a reasonably complicated language. So that's cool. Here is another grammar. Another question that you might be asked is what language is accepted by it? So here we go. Either in English, in set notation, in mathematical notation, however you would like to answer. How could you define this language? My recommendation for where to start deriving some strings. Utilize different sequences of these productions and see what happens.
And it would be A the end, A the end and B at the end with N equals M. Because the same number of A's, the same number of B's.
Do all of the A's have to come before all of the B's? Is there any possible sequence of productions that would produce A's after B's?
Yeah, it'd be any number or like any order.
Can we start with a B? Yes.
That's pretty much what I had, it needs to start and end with a B, but other than that, it just has to have the same number in between.
Yeah, it's interesting. So starting with some of the derived strings, we could derive ABAABB. We could derive AABABB. We could derive ABABAB. What do we notice about how this could map to some kind of construct that we've seen before? Just like we had a grammar in the motivation slides that mapped to curly braces. What is this map to?
Question.
So we had, let's actually go back to that slide for a second. So here we said that A to the N, B to the N was a language where we could replace A's with curly braces. And now we had nesting control structures. So now we could say open curly brace, open curly brace, open curly brace, close curly brace, close curly brace, close curly brace. And that allowed us to represent nested control structures. If we wanted to map this to something like that, what would the grammar that we just looked at, what would that map to in terms of something that we've seen before? We were to replace those A's and B's with something else that we've seen before. What would that allow us to represent?
This is gonna be like a weird way to explain this, but you know, like the valid parentheses probably solve the stack.
Yes.
Kind of like this, but with A's and B's.
Yeah. It's actually exactly mathematical parentheses. If we replace A's with open parentheses and B's with closed parentheses, this is every legal way that you could set up some sequence of parentheses. We know the first character that we have to see is an open parenthesis. If we see a closed parenthesis before we see an open parenthesis, we don't have a legal mathematical expression. We have to have seen at least more A's before we see a B. So we can't have something like ABB, even if there's an A at the end of that, etc., because there are now more closed parentheses than we have open parentheses. We must open something before we close it. So this is very interesting. Right, we have open, we close the thing that's open, we open two, and then we close those. Open two, close one, open a second again, close the second, close the first. Open, close, open, close, open, close. You can see how those rules now derive that. And it's actually very simple to represent in grammar form. Every legal possible set of parentheses can be defined by these three small productions with a single non-terminal. What in the what, how, why, I'll leave you to kind of ponder why that is so easy to represent. As a context-free grammar. Note that we can now have multiple non-terminals in a single production as well. So we're gonna go into something that is an interesting problem that will turn into a much bigger problem the more we look at it. So trying to figure out whether a particular string is in a language defined by a context-free grammar is a much harder question than it was in a regular grammar. Anyone have a sense of why that is? I give you a string, like let's start with this grammar. I give you some long string of 100 characters, and I ask you, is this string producible by this grammar? Why is that a hard problem? Yes. Super tedious, but how would you algorithmize that? How could you write an algorithm to actually be able to answer yes or no? This grammar can generate that string. Kind of brute force, right? You have to try everything because you don't really have an easy way to stop early. Because if a non-terminal comes first, how do you know that that non-terminal can't eventually generate the character that you want? In a regular grammar, you had a way to either start at the beginning or start at the end and start parsing one direction. So you could map easily a terminal to what terminal you were expecting. So you knew exactly which subset of that you could apply. So it ends up being quadratic in the worst case with a regular grammar. But here, it's exponential. We have to try everything, unless we have a way of determining that in a more complicated manner. This is going to lead us down a rabbit hole toward your rest of quarter project. But let's start by just introducing the problem of why this is so difficult, what this kind of looks like. So we're going to look at some preliminary work before we dive into that. Let's first define the concept of an ambiguous grammar. This is a terrible, terrible thing. We don't like ambiguous grammars. If two grammars are ambiguous, that means that given a string, we can produce that string via following multiple different production paths. As an example, here is a grammar, and I've separated out not allowing for ors in this grammar. But think about trying to produce the string AAB from this grammar. So we want to, via some sequence of productions, create this. See if you can come up with multiple ways to do that. If this grammar is ambiguous, then you can apply these rules in multiple different orders to produce this string. Anyone see one way to do it? Go straight down the order, 1, 2, 3, 4, 5. So let's start with S. We'll apply 1, and that gives us AB. We apply 2 to replace the A with A, we still have our B. We apply rule 3. This replaces the A, capital A with a lambda, so we have A, capital B. Then we have rule 4, which tells us we replace the capital B with capital B lowercase b, A, B, B, and then rule 5 says we can get rid of the capital B, and we end up with AAB. Perfect. Is there another way we could do it?
Doesn't look like it.
What if we start with rule 4? Start with rule 4. Start with rule 1 still, but then we go to rule 4. 1, A, B, rule 4 from there.
You 1, 4, 5, 2, 3, or 1, 4, J.
A, B, B. And now we can apply rule 5 to get rid of the B. We have capital A, lowercase b. Then from the capital A, we can apply rule 2. That gives us lowercase a, capital A, lowercase b. Then we apply the rule that gets rid of A's, the 3, and we end up with AAB.
Also, does it not matter what order you process your non-terminals in?
Correct. Well, that's the idea behind a leftmost or rightmost derivation, is we're gonna start with saying the path to determine this is going to start either from the left side. We're gonna resolve our non-terminals from either the left side or the right side. Because if you kind of do it willy-nilly, then you're forced into brute force, which is disgusting complexity. So the first way to reduce that complexity is either to start at the left side or start at the right side, resolving non-terminals. So we see that there was a different way to do this based on the order in which you resolve your non-terminals. Here we kind of went left to right. Let's deal with this A. Let's deal with this A. Let's deal with this B. Let's deal with this B. We're done. And this went kind of from the right side, where we said, let's resolve this B. Let's resolve this B. Let's resolve this A. Let's resolve this A. We got there. So via 2 different forms of attacking this from the left side and the right side, we ended up with different sequences of productions that could generate this. And we will see momentarily why this is really bad.
Also, illustrated, so.
Yeah. You could. Yeah, these are just 2 examples, but there are others. So ambiguous grammars are bad. I will leave it to you for now to think about why that might be before we go over it. So here's what we just did. So we can eliminate ambiguity if we force an order in which non-terminals are replaced. So we can either think about starting from the left side or starting from the right side. If we force us to start from the left side, then that ambiguity is gone. There's only one way to produce AAB, if you have to always resolve the leftmost non-terminal first. Same with the rightmost non-terminal first. So if we continuously replace the leftmost non-terminal, we call this a leftmost derivation. If we continuously replace the rightmost non-terminal, we have a rightmost derivation. If you have an ambiguous grammar, anyone want to take a guess at what happens programmatically? If you were to apply the rules of a grammar of a programming language, what happens if you have an ambiguous grammar? Or what could happen? Kind of tricky to think about. But the answer is basically that given the same starting instruction, the same statement, that could map to multiple different instructions. Given a different compiler or a different way of doing this. You would find a way to interpret different statements in the same statement in different ways, which should not be. There must be exactly one logical meaning for every statement that you write in a programming language, only one way to interpret it. If there are multiple paths through a grammar to the solution of what does this do, then you end up having different interpretations of the same statement. So we need to get rid of ambiguous grammars by the time we're talking about programming languages. So we'll come back to this problem later on in the course. But we will see kind of how this rears its head when we start talking about compilers. We're out of time. We're gonna come back to this tomorrow. Remember that we have an assignment that is due tonight. I will get the next assignment up. Be prepared for the hardest assignment so far in the class. There are lots of, not lots, but there are some proof-based questions applying the pumping lemma that we've talked about. So please do get started early. I anticipate that just about everybody is gonna get stuck on this at some point, in some way. The earlier you start, the more I'll be able to help you through it. And I'm more than happy to do that. I do have office hours starting now in my office. If you have any questions on the current assignment or anything else about the class. If you disagree with any scoring on the exam, please let me know. I am happy to take a look at and hear your argument and your perspective. I can't guarantee that I'll make any changes. But I would rather hear your argument than not. I find that frequently I do agree with students. If you think that it's unfair, it may be unfair. Let me make an executive judgment on that. All right, see you all tomorrow.